Hi, everyone. We really appreciate you being here today, and we hope you'll get valuable information about understanding names with neural networks during this webinar. My name is Allie Devine. I'm the event manager here at BASIS. I will be your moderator today, and I'm going to make sure all your questions are answered. I'm sure you've already noticed, but everybody is muted. So if you have questions anytime during the presentation, please feel free to ask them throughout. However, we will wait until the end to answer them. To submit a question, just click on the Q&A button at the bottom of your screen. Now, when the webinar ends, you'll be directed to a survey. I would love it if you would take just 1 minute to let us know your opinion. It really helps us to learn what you're looking to get from us for future webinars, and we are planning a lot more. This webinar is being recorded, and we'll be emailing out the link tomorrow to everyone who registered. So if you find it useful and informative, please feel free to share it with anyone who might be interested. Now, while we wait for a few more people to join, I'm going to spend just 2 minutes telling you about BASIS Technology and Rosette, which is our text analytics brand. BASIS Technology has been around for 25 years, and our mission has been focused on getting structure and meaning from unstructured text. So reports, articles, social media posts, comments, that kind of thing. We pride ourselves with providing a high quality, carefully curated and tested set of text analytics and natural language processing capabilities. We also pride ourselves with comprehensive NLP coverage. So this includes a breadth of capabilities from providing the building blocks of text analytics that are language identification and morphological analysis, to delivering advanced tools like cross-script semantic search, and of course, cross-script fuzzy name matching. All the Rosette capabilities are highly adaptable with easy tools for domain adaptation and have many options for deployment. We work with our clients to engineer the best possible NLP solution for their needs using every possible data source to make their AI smart and resilient. Now, the reason we're here today is because we've also put a lot of effort and R&D in developing a highly sophisticated and fuzzy name matching algorithm that doesn't rely just on rules, but includes machine learning models. So this tool is capable of catching many name variations and phenomena. It was developed for the US government, and it's been used in immigration and counterterrorism applications, but is also now being used in onboarding, AML, and KYC systems. In fact, today we'll be showing you the more technical algorithmic side of the product, and we'll share with you some of the research projects that we've recently been working on. So that's all I'm going to say about Rosette and BASIS Technology. So let's kick this off. This webinar is planned for 60 minutes. There will be a 40-minute presentation followed by a 15 to 20-minute Q&A session. So let me introduce your host for today's talk. Kafir Bar is the chief scientist of our text analytics team and the head of R&D. He's spent many years working in a wide range of natural language processing disciplines, and he plays keyboard in 2 rock bands. Philip Blair is a senior research engineer who's been with BASIS for 4 years. He's the critical link between our R&D and product teams, and when he's not working, he's an avid traveler, sans 2020, although he's currently in Paris during the pandemic, and his goal is to eat something in every country around the world. And Carmel Eliav has been at BASIS for 2 years as a research engineer. She's been mainly focusing on writing the neural of our name matching algorithm, and she served as an Army intelligence officer for 8 years. Now, since names are hard, and I know you don't want to hear about fuzzy name matching and deep learning from me, I'm going to let these 3 great minds tell you about it. So Kafir, why don't you start?
Thank you. Thanks for the introduction, Ali. So let's kick this off. So processing names, important for many applications, including financial compliance when banks need to match records based on person or company names, or even search a large international list of high-risk people, what we would typically call a watch list. Now, the problem is that there are many names out there, right? There are many variations, nicknames, not to mention the different ways for how to transliterate those names and write them in different languages. And name search is also important for border control, for example, when someone arrives with a foreign passport and a name written both Latin script and the original language, and then searching for that name in a large watch list, or matching the name against some existing records in a large knowledge base requires a more comprehensive technology than just a simple text lookup procedure. So the task is what we're dealing with is called name matching, and it starts with a pair of names for which an algorithm needs to calculate a matching score, and that score will reflect how similar those names are. So this is just an example here, and you can see different variations of President Roosevelt. So the first one on the left side is written in Latin script, and it's a full name variation, whereas the other two are written in completely different scripts and languages, and we still want to match them against the original name. So when matching two names, one would face many challenges. There are phonetic challenges, as you can see here, spelling differences, missing components, and of course, there are challenges of matching the same name, but when it's written in different scripts and languages. Now, in addition to matching pairs of names, so we have plugins for search platforms, search engines, such as Elasticsearch and Solr, as you can see here. And this product is called Rosette Name Indexer, or RNI, and it enables name search in all these platforms by addressing all the challenges that I mentioned before, using some machine learning algorithms. With RNI, given a name to be found in a watch list that is stored in one of those search platforms, search engines, RNI runs in two passes. We have the first pass where it generates a relatively large set of candidates. And then in the second pass, it uses different types of algorithms to produce matching scores for all those candidates, so that we can filter out those candidates that their score is below a certain threshold. Now, our name matching algorithm in general supports different entity types, like what you see here. We have person names, organizations, locations, dates, addresses, and we also support about 18 different languages at the moment. So the algorithms that we use to do the matching, we use different types of algorithms. And for example, we have simple misspellings. So we typically use eddy distance calculations like Levenshtein distance, and for misplacing name components, and to support the variability in naming convention in different cultures, different languages, we use different rules to do that. And then we have phonetic models in order to match names that have a similar sound, including names that are written in different scripts and languages, as we mentioned before. We have semantic algorithms too, and they're usually based on word embeddings, and we use them to match name parts that have similar meanings, for example, university and college, or LTD and Inc. for company names. And our users have full control over the configuration of those algorithms and the way that we aggregate their scores into a single score by assigning weights for the individual algorithms based on their need. So in what follows, my colleagues here, Philip and Carmel, from our research team, will talk about our journey in building a data-driven neural network for phonetic name matching. So we're going to focus on that here. And we will focus on name pairs in which one name is written in Japanese katakana and the other one is written in Latin script. So that will be the focus of this talk. And we will begin with explaining our relatively simple data-driven approach based on Hidden Markov Model, and then on to more robust technology based on recurrent neural network, RNN. And finally, we will mention our recent model based on a convolutional neural network just to balance between accuracy and matching speed performance. I have to say that this session will be technical, and we'll focus more on the algorithmic part of the product and less about how to operate the product and its main functionalities. So yeah, I think I'll let Philip take it from here.
Great. So thank you. So as Kfir said, we're first going to start out by looking at a more traditional way to do data-driven name matching with hidden Markov models, or HMMs for short. So this is not going to be like a deeply mathematical overview of how they work. It's mainly meant to just give you some intuition to motivate our later discussion about what the shortcomings of these are and how we can address them with deep neural networks. So when we want to match an English name versus a Japanese name, the first step is to actually learn how to model the transliteration process from English into Japanese. And so there's two steps to doing this with an HMM. First, we need to model the monolingual dynamics of the English language. And the way that we do this is we simply take a big data set of names and we just look at the probability of one character following another. And so you can see how we can build up this big transition diagram containing all of these likelihoods. And then a name just becomes a walk through this graph. So we're going to focus in on John here. And then in order to actually do name matching or name transliteration, what we then have to do is learn how to associate each of these letters in English with corresponding letters in Japanese. So again, we take a data-driven approach to doing this. I don't want to get too much into the details here, but the upshot is that we're going to end up with an association like this, where we have different probabilities of different Japanese letters corresponding to each English character, and you can see the bolded states here being the proper transliteration for John. So once we can actually model this sort of transliteration process, the scoring procedure becomes rather straightforward just by the nature of the probabilities of this type of setup. We simply model the probabilities of observing this name John and compare that to the probabilities of that corresponding to the given Japanese sequence. Combine those together and we come up with a score. So at this 10,000 foot level, that sounds relatively straightforward, right? Except if anyone here can actually read Japanese, you might notice something a little awkward about this diagram, especially given how I said we construct it. So let's focus on these first two characters here. So for those of you that don't speak Japanese, I provided a table explaining what might be a little awkward about this. Remember now that these gray states are modeling the dynamics of English on its own. And so what that means is the state that we have for the letter J represents all possible instances of the letter J in English. Similarly, the letter O represents all possible instances of the letter O in English. However, the transliteration that's appropriate here really requires utilizing this context of an O following a J, because as you can see in this table, the choice of Japanese character that we would select for that type of situation is dependent on that context. However, the state itself doesn't really reflect any of that contextual information. It's a context-free representation of the letter O. And so this is just a single instance of a broader problem when doing cross-script name matching, and that is that the correspondence between characters in your source language and your target language are very rarely one-to-one. And so, this specific issue can actually be somewhat addressed with HMMs. You can essentially add new states to your HMM that model these types of diphthong instances. However, that does require someone to actually have some domain expertise in the specific language pair that you're looking at in order to know which new states you need to be adding, because that's not a data-driven process. But what's even worse is that there's actually some phenomena that you can't even model with these extra states. So an example of this would be in Arabic. There's a phenomenon in which a suffix on a name can affect the pronunciation earlier on within that name. So the best way to illustrate this to an English-speaking audience would be if you add the letter Y to the end of the word photograph, the pronunciation becomes photography. And so the presence of that last letter affects how we're going to pronounce that middle syllable. And so roughly speaking, this same kind of phenomenon is something that you would ideally want your name matcher to account for. So as such, we really would like a more general way of modeling context when doing name transliteration and by extension, name matching. And the unfortunate fact is that solutions to this problem with HMMs either don't scale to long sequences or they're just too computationally intractable to be usable. So instead, let's try something different. Let's think about how you as a person would do transliteration. So first, let's think about what the HMM is doing. And it's a process that looks kind of like this, where you're going to look at the English name, a small piece of it, turn around, write the corresponding transliteration for that small piece, turn back around, read the next one, and so on and so forth. Now, that, for one, this is actually slightly more flexible than the HMM because you're not, you're allowing these chunks to be more than one character long. But even setting that aside, this is not really a natural way of doing transliteration, right? I mean, you're not going to simply just read the first character and turn around and blindly write the transliteration, right? And so to further motivate what the shortcoming of this type of formulation is, let's think about at like an abstract level what the HMM is actually doing. So effectively, what you're doing here is you're taking your sequence of English characters and you're associating like 0 or 1 Japanese characters with those English characters. And this is effectively a form of sequence tagging. And so what this means is that we lose this flexibility of freely associating certain subsequences of the name John with certain pairs of letters or single letters in Japanese, which really we would like something that allows us to group pieces of the name together in a much more natural way. So if sequence tagging is not the answer, what is? Well, again, let's think about how you would transliterate a name. Now, assuming, of course, that you're well acquainted with both languages, let's imagine that names generally aren't too complex, right? You can conceptually think that you can read a name, remember it, turn around, and write down that transliteration. And so effectively what you've done in this process is somehow condense the name into a single memory or like a portable notion of that name that is suitable to be used to produce this transliteration. And that single notion contains all of the contextual information about all of the different pieces of that name. So ideally, this is something that we would like to replicate with a machine learning approach. But the question is how to actually do that. And so the good news is that we need to look no further than work that's been done on neural machine translation. So this is a similar problem where instead of transliterating a single name from one language to another, you're translating it to an entire document. I mean, it's Google Translate, basically. So for neural network-based approaches to this, what they use are two pieces that are essentially analogous to what we just described, where you have an encoder module that's going to read in each word in your source language, build up some notion of the entire document, and then turn around and pass it to a decoder, which then is going to produce the translation of that source document word by word. So, because of the earlier described issues with HMMs, we felt that this would be a natural type of setup to try for doing names transliteration as well. So just to get slightly more technical, what do these encoder and decoder modules actually look like? So traditionally, they were what were known as recurrent neural networks, or RNNs. These come in a variety of different flavors. Now, the important thing to remember with an RNN is it's a piece of a neural network that operates on a sequence of inputs. So what that means is we can feed in succession either the words in a document or the characters in a name or whatever sequence you would like to process. And in addition to processing the individual pieces of that sequence, it will build up some notion of the sequence as a whole. So we used a specific flavor of an RNN known as a long short-term memory network, or an LSTM, which again is simply just doing this, this process of building up a contextualized representation of the entire input name. So I think that might have been a lot. So let's actually look concretely at how this looks when we put it all together. So again, similarly to the neural machine translation setup, we're going to have two pieces here. We're going to have an English name reader, which is our encoder, and then we're going to have a decoder, which is a Japanese name generator. And so when we zoom in, we can see that we're going to feed in the English name one character at a time, building up this notion of the entire name as a whole. And then from that memory of the name, that portable notion, we can then produce the entire transliteration using another recurrent neural network. And so intuitively at a high level, you can see how these two pieces are roughly analogous to the two types of probabilities we had in our hidden Markov model. The encoder represents the dynamics of English, of monolingual English text, except instead of being a rigid notion of a state for each letter, you're building up a more nuanced, contextualized idea of how these letters are interacting with one another. Similarly, you have this idea of emission probabilities in a hidden Markov model, which are these probabilities of Japanese characters corresponding to English ones. And instead of fixing those like you do in an HMM, you're once again making it a little more nuanced, right? You're making it, you're asking the question of how do Japanese characters correspond to this name that we've given it. And so because of this ability to model this nuance, this representation is much more capable of modeling things like multi-character equivalence or pronunciation affecting suffixes and so on. So once again, similar to the HMM, we can use the probabilities from the generative model that's being produced in order to produce a score. So again, zooming in, this process looks very similar to the transliteration process, except instead, because we already have the name that we're trying to match, you see that we're feeding in letters into the decoder as opposed to having it produce these letters. Now, the idea of running a decoder in reverse might not be totally intuitive at first. So let me try to better explain what that means. So in order to wrap your head around this, you have to remember that the decoder is not a black box, right? Like it's not just an unobservable thing producing characters. Instead, at each point in time, what it's going to do is produce a probability distribution over all possible characters in Japanese that could be at that point in time. Then typically we look at the most probable character at that point, and that is our predicted character. So in effect, you can interpret the output of the decoder as being simply the maximum likelihood, if you're familiar with that terminology, estimate of this conditional distribution in the top right. And that's really just a fancy mathematical way of saying that what the decoder outputs is the name that is most probable given the English name. But the reason why I want to hammer on this point is that once we make this intuitive leap, we can then start thinking about what other ways can we use this probability distribution. And the way that we do that for name matching is instead of accepting those outputs as being gospel, we're going to instead take we're instead going to observe these distributions and then see how well our given sequence aligns with these probabilities. And the way that we do this is with a measure from information theory known as perplexity. So at a high level, what this really just means is how surprising is this sequence compared to what we would expect the model to be producing. because intuitively, if our model is well trained, we would expect the correct transliteration of a name, i.e. a matching name, to be something that's not surprising for the model. Alternatively, if we feed in a name that is completely different, we would expect that to be a highly surprising output for the model to produce. So we simply summarize it with this perplexity measure that I'm not going to explain what it all means, but just take my word that it does measure this notion of surprise. And then because we want less surprising names to be higher scoring for our name matcher, we take the reciprocal of it. And so voila, we have a single measurement that we can use to quantify the degree of matching similarity between an English and a Japanese name. And now what's really cool about this is that unlike the HMM, there was no need to worry about this action at a distance of suffixes, but more importantly, there was no need for a domain expert to sit down and say, hey, JO really needs its own state inside of the HMM. The neural network is able to learn that entirely on its own. And so the amount of effort for adding support for matching new languages is greatly reduced. So this work that our team did was inspired by a customer who came to us with a list of names that were being incorrectly matched as a match on an internal data set of theirs. So they gave us this list. We built this algorithm using our data, and then we evaluated that list, and we found a 75% error reduction on that data. Of course, your mileage may vary because you're not that customer probably, but what we will say is that on our internal evaluation data set, we did see a 10% accuracy boost using this technique, which might not sound terribly substantial, except because our HMM model isn't bad in the first place, we typically only see improvements on the order of like 1% or less whenever we tweak it. So to see a 10% accuracy boost was certainly a very substantial piece of progress for us to have. So now that I've sold you all on neural networks, the bad news, there's no such thing as a free lunch in this world. So there is a cost to all of this, and that is speed. So when we compare our neural architecture to the HMM, you can see that there is a slight slowdown on the order of roughly 25%, or 25 times slower. 25% would be great. Yeah, so, because this is a more sophisticated technology, it's not like we expect it to be as fast as the HMM. Like, that's not our goal here. And depending on your application, I mean, the throughput really might not matter, right? But at the same time, a 25 times slowdown is really a tough pill to swallow for pitching this as a replacement for the HMM, especially for our customers that really do care about speed. But the good news is that not all hope is lost on this front, as Carmel will now describe.
Hello, everyone. So as Philip mentioned in the previous slides, and if you're looking at a more detailed version of our seek-to-seek architecture, there are three components: the encoder, the decoder, and the attention. Each is a separate neural net with its own purpose. The encoder encodes the information of the English input name, and the decoder generates the corresponding katakana name. The attention determines which information is important in the encoded sequence on each character generation. Attention is often used in sequence-to-sequence problems, and it allows the decoder to dynamically attend important characters from the input and to automatically increase their weight when decoding. I'm not planning to go into more details here, but if you guys are interested, this idea is explained in different resources online. LSTM is a natural architecture for sequential tagging and sequence-to-sequence problems, since LSTM was designed to handle data that is encoded with temporal information, like text. However, LSTMs are relatively slow due to the large amount of calculation that takes place during inference. And the attention part makes things even worse. So the first step was to get rid of the attention model and to let the decoder use only a static vector of information from the input text. That didn't change much, and we were still looking at a relatively slow process. Since in our case, both the encoder and the decoder are LSTMs, we were looking for ways to reduce the number of calculations by considering different architectures, at least for an encoder. Then we decided to experiment with a convolutional neural network, which is a different kind of neural network that people typically use for computer vision. For now, the decoder and the score function remained untouched. So what is a CNN? CNN is a neural network with weights, loss function, activation function, and so on. But its unique design enables recognizing patterns or features over space, or in other words, special features. Also, it's less about encoding temporal information and time series. CNN layers contain filters, and each filter is responsible for detecting a different pattern. As we go deeper into the network, the filters are recognizing more detailed structures. In computer vision, they could be objects, parts like wheels, wings, eyes, and so on. The nice thing about CNN is that it may recognize these features in different locations in the input without seeing them in that particular location during training. In other words, those features are location and rotation invariant. For example, in the following picture, the filters in the first layer may detect lines, and the filters in the next layer may detect larger structures like nose, ears, and mouth. And the last layer may detect the whole object. So let's go back to our problem. How do we use CNN in NLP? We can look for patterns in the text. As always, the first step is to run our text into turn our text into vectors. Typically, embedding is the way to go, but of course, we can vectorize the text in any way we want, like one-hot encoding, for example, as long as we have our text represented as a matrix. Now, the filters in the layers can look for patterns in the embedding matrix the same way as in pixel matrix of an image. The only difference is that every filter is in a different size, and instead of detecting structures, they are detecting consecutive token patterns. For example, if a filter has a width of 5, then it can see 5 consecutive tokens and store for them in the text. You can think of it as a combination of a lot of different n-grams. In the following example, in the sentence, wait for the video and don't rent it, one filter will detect the combination wait for, and another filter may detect the combination wait for that, and so on and so on. There are a lot of architectures out there, right? So why did we choose CNN? Well, speed. CNNs are faster by design, and the computation in CNNs can happen in parallel. Same filter applies to multiple locations of the embedding matrix at the same time, while RNNs need to be processed sequentially, since the subsequent steps depend on previous one. So we know it's faster. Why wasn't it our first choice? Context. Because we process each character separately, we lose the valuable information that can be extracted from context. The order of the characters in the name is important. Take, for example, the combination of the characters C and H. The transliteration of those characters separately and together is not the same. So to solve this problem, we use positional encoding, which is basically a standard embedding layer where the input is not the character itself, but the position of the character within the token. We calculate positional embedding and standard embedding separately, and some both matrices. But as a wiser man said before me, there is no free lunch, and we had to pay the cost. I'm sorry. Let's look at our results. We tried 2 different CNN architecture with various hyperparameters, and we did manage to reduce the speed significantly, but we had to pay the price in accuracy. In the following table, we have the architecture type, the improvement relative to the HMM, and the speed relative to the HMM. We can see that the accuracy results of the CNNs are good, but not as good as the LSTM. But we can also see that there are good news, and the speed performance is much, much better. So that's it for me. I'm going to pass the torch to Kfir. Thank you.
Great. Okay. Thank you so much, Carmel and Philip. Let me try to wrap this up for now. So I guess the main takeaway is that name matching is still an open problem, right? We can still improve name matching, at least for some specific pairs of languages. Like always, like you've seen here, improving accuracy with state-of-the-art neural networks comes with a cost, which we pay in speed performance usually. But luckily this time we're able to find a solution in the shape of a different architecture, specifically here, convolutional neural network, that captures most of the information that we need. But the plus is that it's much faster. So our plans for the near future is to get this technology and try it with other language pairs. Right now we're working on Arabic, for example, as well as maybe experimenting with a fully end-to-end data-driven name matching algorithm that replaces manual processing, fine-tuning, and configuration. That's something that we'll be working on in the near future. We have other activities in our names team, improving the algorithms and adding support for other languages like Hebrew, for example. And so we will keep you posted on our progress in our next research webinar, hopefully sometime soon. And I think that's it for the presentation, and I will give it back to Ali for some Q&A.
Great. Thank you, guys. That was very interesting. So that's it for the presentation. Now it's time to ask any questions you have. Click on the Q&A button at the bottom of your screen to submit your questions. We do have a lot of people on today's webinar, so if we don't get to all the questions today, please feel free to reach out to us. While we are waiting for questions to come in, I do want to remind you that this presentation is recorded and a link will be emailed to everyone who signed up. So please share it if you enjoyed it or if you think somebody might be able to get something out of this. Also, if you aren't able to stick around for the Q&A session, when you leave the webinar, you'll see a survey pop up. Please just take 1 minute to let us know your thoughts. Your feedback is so important to us and it allows us to continue to improve all the webinars that we're putting together. And speaking of, tomorrow we'll be hosting a webinar called Smart Matching for Screening, which is it's more of a high-level overview of how smart name matching is deployed in critical business systems. So if you want more of a high level rather than the technical algorithmic version, tune in tomorrow. So you can find all the details about that and a few other webinars we'll be hosting at basistech.com/events, or you can follow us on LinkedIn or Twitter and we'll be announcing them there. So great, let's get to the questions. All right, Philippe asked, have you considered using HMM first to make the decision for easy examples and ISTM for harder examples?
That's a good question. I can take it, but you guys weigh in if you have anything to add. That's a great idea. We haven't done that, but so we'll have to consider how we detect what are those easy examples and what are the harder examples. But combining models is definitely something that we would consider, and we're doing that in other products. So that's definitely a viable approach.
Does anyone else want to tune in, or Philip, Carmel? No.
Yeah, no, I think that's mostly it. Like, yeah, the big question would be, how do you detect those easy examples? I mean, I imagine, you might be able to say if it's really confident, the HMM, then we can believe it, but we would have to measure that and determine whether that's true.
Yeah, I agree. And it was a good question also.
Yeah.
Okay, Omar asks, what are some areas you focus on from an ETL level to ingest the data?
Anyone want to take it? I'm not sure I totally understand the question.
Yeah, me too. Can you repeat that, please?
What are some areas you focus on from an ETL level to ingest the data? Okay.
We'll need some clarification.
Omar, if you could clarify, that would be great. Are the models pre-trained on specific data sets?
Yes. So our models are trained on some pairs, a list of pairs of names. Specifically here, we're talking about this work on katakana, right? Japanese and Latin. So we have large list of name pairs that we train our model on.
Okay, and Jennifer asked, when you said that the system learns on its own, does a human still need to check the results?
So, yeah, I mean, from a quality control perspective, I mean, you certainly would want to verify, yes, but at a high level, the way that the machine learning problem is set up, you're essentially, well, if you're familiar with the terminology, you're trying to minimize a loss function, right? And the loss function here is the reconstruction of the Japanese based on the English input. So in essence, once you've confirmed that your model is producing roughly reasonable output, you can then start running something like a hyperparameter search that would then allow you to determine, you know, once that loss function has been sufficiently minimized, it's pretty automatic. Again, once you've made like the ballpark check that it's basically learning the correct thing, right? And then of course at the end, we take that model and then we run an evaluation on a held out data set. I don't know if that answers the question, but.
Yeah, I would like to add, we have a very thorough system of evaluation. So it will be nice to have a human. It's always nice to have a human, you know, to take a look on all the results. But sometimes if you're testing your data on 100,000 name pairs, so it's just, you can't. So that's why we have a very thorough system of evaluation. That's it.
Okay. And Jose asked, isn't it better working with lemmas?
So typically in natural language, in languages that are that have rich morphology, it typically works better with anything with lemmas. But I think in this case, I mean, we're talking about names, so it would be more difficult to define what is a lemma for names, right? So we probably need all the different parts of the name. So that's why we're not using lemmatization. Now, having said all that, with the neural networks, a neural network approach for any problem, I mean, there is a belief that you typically want to give it the raw data so that it will focus or it will learn by itself what are the best or the main features that will help this that will help in this specific problem, right? So again, lemma is a great idea, but for names, I guess it's more problematic.
And somebody also asked, can we try it on your cloud?
So the first model, the HMM model is available. It's a full product, and the model that Philip described, sequence-to-sequence LSTM based model, is available for Japanese and Latin, but we're still not. We haven't delivered into production environment the last model that we talked about, the convolutional neural net model. That's what I have.
Great. And how does the quality and the amount of data set impact the accuracy of the final name matching DL model?
Philip, you want to take that? I see you are clicking.
Yeah, I mean, so, well, the short answer is I don't think that's something we've carefully measured at this point. However, the at a high level, I mean, of course, what goes in is what comes out, right? I mean, assuming that you can have some amount of variation in your data set, right? Like you could have slightly different transliterations for the same name, and that wouldn't necessarily be a problem per se. However, I think that you know, if the question is about like, do you need to actually go through the work of curating a reasonably accurate list of name pairs? I think the answer is yes, even with the deep neural network approach. Yeah.
Great. How do you source the name data? For example, kanji name lists.
That's a good question. So it depends, right? We have a data team, and specifically this project was triggered by a client. The data is something that we collected, so specifically for every language, we're looking for different sources that are available, and if not, so we're actually annotating and creating our own names.
Great. How many pairs would you recommend for high accuracy? And are there publicly available data sets for cross-lingual name matching?
Well, in the Japanese LSTM, we trained with 33,000 pairs, which was actually, it worked great. It wasn't a large number or a small number, it was great. We're now trying to work with Arabic, and there we have 100,000 pairs. And the interesting thing about it is that the results are basically the same. I mean, relatively the same. It's a different language, but the results are relatively the same. So that's an interesting point. And I want to add that about the quality of the names, it was related to the other question. You need to have like a very wide range of name pairs. If the same, never mind. I'm going. I will stop myself. But the quality is important, and we had 33,000 name pairs.
If I could just add on.
I'm going to stop myself.
Yeah, just to add on to that, I mean, like the amount of data you need is also definitely a function of which of these algorithms you're trying to train. You know, if you are training an HMM-based model, the data requirements might be, you know, somewhat less than for the LSTM, for example. But of course, I mean, in the data science world, more data is always better. So, yeah.
All right, let's get back to Omar's question, and this is to clarify the ETL question. So we use fuzzy search matching for OFAC engagements. We normally ingest records like wire payments to find parties and compare them to OFAC lists. Is there any way to stage better, better the data for calculation or comparison? Is there any data enrichment prior to ingestion?
So I would say that one thing for sure is if you can figure out the type of the entity, right? So that we know that this is an organization, so that can be very helpful because we have different types of algorithms going back to the product and not just the model that we were talking about here in this session, right? So we have other algorithms that we mentioned at the beginning of this session, and like rules. So all these rules are based, they can benefit from knowing the type of the entity. So that's for sure one thing. I would say also that, I mean, if you have different alternatives of that name, so let's say you're extracting, I don't know if it relates to the scenario that Omer, you're describing, but in general, if you're extracting those names from running text, right, from unstructured data, so linking those names or grouping them into one cluster. So one cluster of names that refer to the same entity, the same identity, basically, may help, because then you have different alternatives which you can use with the name matching capability.
Great. And Yuri asked, did you do some kind of data augmentation in order to generate new pairs, like introducing typos in the original string?
So we did some work. I don't know, you guys, if you know, I mean, so the data that we are working on was generated, again, by different, taking different approaches. So we're collecting names from different dictionaries and lexicons, and then we are transliterating them, sometimes manually, sometimes we're sourcing some existing resources. And then, yes, we're doing, we're doing different combinations, right? Sometimes we add some typos into the names, and sometimes we take a name. Let's say we have a name that is composed of two components, like first name and last name, and we're switching between them. We're doing different combinations between different names, and we're switching between family names. So we're doing all this kind of augmentation stuff to enrich our list of names for training.
Okay, and are you using transfer learning, or do you train from scratch with your own data?
Train from scratch.
So at the moment, we're not using any transfer learning. However, that's something that is definitely something really exciting for us to explore. So, for anyone who's not familiar, transfer learning is this idea of reusing parts of an already trained machine learning model to reduce the amount of data you need to add new tasks. And one thing that's really cool with this specific setup we have here is, conceptually, when you're transliterating from English to Japanese versus English to Arabic, do you really need a different English reader module? I mean, not necessarily, right? Or do you really need a different Japanese decoder module? Not necessarily, right? And so that kind of question of, could we maybe just use transfer learning to try to get a fully cross-lingual name matcher for language pairs that we don't even have data for, is something that's really interesting that we would like to explore. But for the moment, no transfer learning.
Okay, and what kind of ground truth are you using for validation?
So we're using, the same data that we have. So we're splitting it usually into like the training set and development set, testing set, which we use for doing validations. And then the way that we are calculating accuracy here, specifically the numbers that you saw here. So if you remember our LSTM model, for example, and the CNN model, so it has the capability, both have the capability to actually transliterate the names, not just to produce a score. So they take a name, right, and they can transliterate the best name, I would say, or the best version for the input name. It's not doing only that. It's actually it's producing probabilities, right, and distributions for all the different names that you could compose in the output. So what we do, we came up with this formula for calculating the score, so that score, that perplexity, as Philip described. So we take that score, we calculate it exactly for the name that we want to extract there, one of the, I would say, the target name, or the target part of the name pair, and then so we take that score basically, right? And if it passes a specific threshold, so we say that it's a match, right? So if it's a match, so we count it as 1 rather than 0, and we can calculate accuracy. So this is how we do that. I hope it's not too complicated.
Okay, and with Japanese matching, Chinese and Korean name transliterations often generate a lot of noise using the language detector. Will the new model bring improvements in that area?
So I think the question is where that noise is coming from within our model. I mean, presuming that it boils down to the the phonetic-based model having noisy rules in the HMMs, similar to the correspondence issues I described before, which I certainly could imagine happening with at least Japanese and Korean. I think we would expect to see some improvement, but again, the work that we've done so far has focused on English Japanese and English Arabic, so we can't definitively answer that at this point, but I think if we had to conjecture, it probably would improve those results. I don't know if either of you have anything you want to add to that.
Yeah, that's good.
Could a similar deep learning based approach also be used to improve your general intralanguage name matching capabilities, or is it mostly impacting cross-lingual use cases?
It could potentially also improve intra-language. Right now, we're only testing it on cross-lingual, but I don't see a reason why it wouldn't.
Sorry, there are a lot of questions I'm trying to get through. Are there scenarios in which the neural network model currently underperforms compared to the current name matcher? If yes, how do you plan to address these?
So I believe the answer at the moment is nothing systemic. So I guess that's the answer, right?
Works great.
Nothing that we've seen so far anyway. I mean, of course, there could be something lurking that we just haven't found yet.
Yeah.
Okay, is there any reporting available to understand the score better? Essentially, we would like to enhance our threshold.
If there is, so the question is, if we have more information about this? Because I don't have it in front of me.
Yeah, so this might relate actually back to the question about ETL earlier. Yeah, for tuning thresholds,
So I can only say about tuning. So yeah, it's a tricky, it's a tricky part, right? And right now, the way to tune the algorithms is basically, to play with the different parameters that we have, and then test it on, real situations. But we do plan, as I said at the end of the presentation, we have some plans right now, only thinking about this, about trying to build a kind of end-to-end name matching algorithm, so that we can actually skip that part and basically let the network or the model learn the entire process without doing any fine-tuning after. And that's learning everything against a specific evaluation set, right? So if you can provide an evaluation set that you care about, so we can basically learn a model and fine-tune it automatically. So that's something that we're thinking about right now.
Okay, I'm so sorry, guys. That's it for the time that we have today. Thank you so much for joining us. We hope you learned something and found this useful. As mentioned a few times already, there's a super quick survey that should take you 1 minute to fill out. Check out all of our upcoming webinars at basistech.com/events, and stay safe and healthy out there. And we hope to see you again on the next one. So thanks. Have a great day. Bye.
Thank you. Bye-bye.